My name is Kelly Paffel. I'm with Invino Engineering, LLC, located in Tampa, Florida. We are an engineering firm specifically for steam and condensate systems. Today, I'd like to talk about installation guidelines for steam heat transfer components. Now, up at our website, we have the full written technical paper for your review. And if you come to our website, which is shown there, www.invenoeng.com, it's best practice number 64. So we have 64 technical papers on steam and condensate systems for your information. But what I want to talk about is the 14 primary factors affecting the performance, longevity, and ongoing maintenance requirements for steam heat transfer components. Steam components have a reliability life of 15 years with today's technology, and we really should be looking at 20 years. With today's technology, we should be able to achieve long life out of our steam components, typically under 300 psi. But some of the things that we need to know on heat transfer components or guidelines, number one, ensuring safety and proper operation of all our heat transfer components. Safety is always the number one factor, no matter what we do. The other thing is knowing the design specifications that we have out there. There's TEMA, Tubular Exchanger Manufacturer Association, API standards, and B31.1, the National Power Piping Code, and the list goes on depending on the industries that we're working with. So the thing that we want to do is be familiar with the design specifications and the codes that are out there today. The guidelines for steam heat transfer, number one, know the the correct steam pressure. The thing is that plant personnel give us the operating pressure. The operating pressure is 150 psi. Well, how do you know it's 150 psi? At this point, I'm going to put in this heat transfer. You don't. The boiler's operating 150 psi, and that's 4 blocks away. It's not going to be 150 psi. The other thing is the components that we have in the system is the strainers, the isolation valves, the control valve all have a pressure drop. And so we need to be designating the pressure to the heat transfer system or devices. The other thing is proper steam line condensate removal. Steam coming down the main steam line, condensation is going to form. And last thing is we want poor steam quality going into the heat transfer. And the other thing is we utilize butterfly or ball valves for isolation. 2-inch and below, ball valves. You know, the technology has accelerated in the last 15 years on ball valves. Above 2-inch, butterfly valves, same thing. Technology and butterfly valves has accelerated in the last 15 years. But to take a look at an example of a heat transfer, and this happens to be a shell and tube, it could be a plate and frame or spiral, any type of steam coil. The thing again, we want proper condensate removal to make sure that we have 100% steam quality going to the heat transfer. The heat transfer was designed for 100% steam quality. Next thing is isolation valve. As you can see here, we are using a butterfly valve for isolation. All steam control valves need a strainer. And look at the position of this strainer. The position of that strainer, the strainer part of it is always on the horizontal plane, never down vertically. This way they'll ensure that there's no condensate buildup in the strainer. The strainer should have a 20 mesh strainer inside. Also always put a blow-off valve on the strainer so the strainer can have PM or blowing down at different times. Next is the steam control valve. And one of the things with the steam control valve is know the turn down of the steam control valve. The other thing is always mount steam control valves in the horizontal plane. And that goes with any isolation valve. Always mount the isolation valves in a horizontal plane, never in the vertical. In the vertical, you can have condensate buildup in the valve during shutdown, and when you open up the valve, condensate will come through and flash and tear the trim outside of the valve. after the steam control valve, expand the pipe at least 1 pipe diameter. How big should the pipe be? If this inlet to this heat exchanger is 8" in diameter, then this piping should be 8 inches, at least 10 pipe diameters prior to entrance into the heat transfer. The other key factor, pressure gauges. Before and after the control valve. So I know what the steam pressure coming to the control valve, and I also know what the pressure drops are through the isolation valve strainer and the control valve going to my process. My process down here needs a X temperature, not pressure, X temperature. Therefore, I need the pressure to give it to the temperature. Then everything will work fine. The next thing is condensation coming out. And the thing is coming down here to the steam trap. But one other thing, up here, the heat transfer needs a vacuum breaker air vent. Air vent to vent the air at startup out of the process. Air is the world's greatest insulator. To make sure I have proper operation, I want to get the air out of the system. The second thing, when the system shuts down, I want to break vacuum so condensate can drain by gravity out of the process. Remember one thing, condensate gets out of the process by gravity, not pressure or velocity. This piping coming down here, this outlet is 1.5 inches, and then the piping should come to an 1.5 inch steam trap. And then making sure the steam trap is sized correctly. Go through the procedures, and we have a best practice on the selection process of steam traps and sizing of steam traps. Again, we utilize ball valves for isolation. The other question is, do we need a check valve? It depends on the system. Recently we put in 3,000 steam traps, and not one of them had a check valve after it. Only put a check valve in if you have backflow that can occur. Another point is to have pressure gauges upstream and downstream of the steam trap, so we know the pressure differential across the steam trap. A steam trap is an orifice. We need to know P1 and P2. Now, the condensate drainage system depends on the operation of the system. And there are systems that we can go into pressurized condensate return systems and elevate the piping after the steam trap back into a pipe rack. But there are also a lot of systems that we have to go by gravity away and to a condensate pump and be pumped back to the boiler room. Therefore, you really need to know the dynamics of the system. Just to go over the points, strainer, we talked about 20 mesh, pressure gauges, air vents, and saturated steam versus superheat. 98% of the process is required saturated steam at 100% steam quality. We talked about heat transfer condensate removal. The other thing I failed to mention is insulate. All heat transfer components should be insulated. Control valve piping, always expand the pipe, at least 1 pipe diameter after the control valve. Vacuum breakers. Number 12, falling factors. Certain processes, we might have to put a falling factor into the heat transfer, depending on the product buildup that we might have. Number 13, always know the codes and the design guidelines. 14, control valve turn down. The valve maximum flow to minimum tells us the turn down. So processes, we never hit the maximum, but we always hit the minimum. So we want a control valve to go to the minimum. Our approach is short term, we do engineering assessments, steam system balancing, look at steam system reliability, and we also provide engineering training. The long term is upgrades, process changes, and we're always there lowering steam costs. Our contact information is filed. If you have any questions, just email us. And I appreciate your time today. Have a great day. And thank you.